Hello, hi Utkarsh.
I sir.
Yeah, maybe we'll wait for 2 more minutes and then we get started.
Okay, sir.
Yeah. Maybe actually I have some couple of things to discuss. This week we had a meeting with NPTEL authorities, all the gate TAs, right, across disciplines. They were saying that these sessions are meant for tutorials, not for teaching, it seems. So the expectation is that the students will come prepared with the topic, and I have to solve some previous year gate questions. That was
Oh,
the expectation, it seems. So what I was thinking is because we started with system of linear equations, today I'll complete what we started, and perhaps from next class I'll start solving previous year gate questions.
correct, sir.
Yeah.
Okay, sir.
Okay. I'll wait for one more minute and I'll get started. Let me share my screen. Is my screen visible?
Yes, sir.
Yeah. Yeah. So in last class we saw conversion of A to low reduced echelon form, right?
Yes, sir.
Yeah. Okay. So I'll get started. It is 6:03. So let me recap what we have been seeing so far, right? We have been seeing system of linear equations. So what is the system of linear equation? You will be given. Sorry, let me take the. Oh, let me take my phone. Okay. Let me increase the width. Okay. Yeah. This is yeah. So what is the system of linear equations? You will be given a set of equations. They are linear in nature. What do I mean by linear in nature? The variables or the unknowns in the equation will have degree 0 or 1, right? Now, given such a system, in the very beginning, what we saw is how can we encode the system in a matrix format? What is matrix format? We need to put it in AX equal to B format, right? In B, you will put all the constants, and mind you, this B should contain all the constants in the right hand side, right? What do I mean by that? If the equation is, let's say, 2x plus 7 by 7y minus 34 equals 0, you need to bring that 34 to the right hand side, and then you will put the constant here, right? Now, next, once you freeze B, you will fix the vector x. Now, you will fix vector in any arbitrary order you want. Here I have put the variables in the order x, y. Once you freeze the order of the variables in the vector, you will start filling in entries in A in the same order, right? Because I have put x comma x, y here, you need to put the coefficient of x in the first column and coefficient of y in the second column, right? I hope this you must be very comfortable now. How to translate a given system of linear equations to matrix format. Next, we saw once you put this in the matrix format, we saw you can simply obtain the solution by taking A to the right hand side whenever it is possible. So what you did, basically, you can obtain the solution to x by this formula A inverse B. Then we saw this inverse is a very complicated operation, and we also saw cases where you cannot find inverse. And here is one such case where you are given a rectangular system. You have three variables and two equations. Because this is a rectangular matrix, you cannot really obtain A inverse, right? And one more solution is when the determinant of A goes to 0. These are two cases where we saw we cannot really apply this formula, so we need sophisticated method, right? And one more solution, one more reason why A inverse B does not work is computation of A inverse, even in the cases when it is possible, is very heavy, right? And because of that reason, we wanted to go to some smarter solutions, right? Then we started discussing about row reduced echelon form, right? I have been telling in last class that once you convert a matrix to row reduced echelon form, finding solution to X is very straightforward, right? So then let me quickly recap what is RREF, right? Uh, where is the RREF structure? Ah, okay. I think this is a wrong PDF. Let me open the right PDF. Oh, I think I did not save the notes last time. Okay. Anyways, let me write the notes now. So then in the last class, we have been seeing RREF, right? What are the steps to obtaining RREF? First, you will create augmented matrix. Sorry. First, you will create augmented matrix, right? What is augmented matrix? You will put A and then you will put B here. Remember that B contains constants after you have taken them to the right hand side. That B you will put as it is. You should not put minus B here. I hope that is very clear to you. Okay. Once you create this augmented matrix, now the second step is to convert this augmented matrix to RREF format. Right. Now I hope you remember what is RREF format. So it is nothing but a structure. I would say it is a nice structure, right? What you should do, let's say you are given this augmented matrix, be it square, be it rectangular, we don't care. What you will do is to first draw a leading diagonal. That leading diagonal, because if it is a square matrix, then it will not touch the right hand side corner, it will end somewhere here. Then we have a couple of tasks to perform on this, to obtain this structure. What is the structure? Um, yeah, entries along the diagonal, you will make it 1 unless it is impossible, right? In cases where it is not possible to obtain a 1, you will put a 0. 0 is okay, but you will put a 0 only when it is not possible to obtain a 1, right? In the leading entry, in the leading diagonal, you will put 1 or 0, and below the leading diagonal, you will make all the entries 0. Above the leading diagonal, you will make it doesn't matter, whatever entries you have, that's perfectly fine, right? Now then we discussed what are all the legal operations that are allowed to convert a matrix to RREF, right? And we saw that these legal operations are inspired from what you do in solving system of linear equations. So first thing is linear combination. Linear combination is any operation of the form Ri equals Ri plus alpha times Rj, right? And alpha can be any real number. Then we saw one more operation. Ah, I have it here. Acha. Okay, sorry. Yeah, I have the note. Sorry. So this is the RRF. I think we saw the structure, and basically then we formulated the set of legal operations. And what are the legal operations? First is linear combination. Linear combination, that is operation of the form Ra equals Ra plus alpha times Rj. Then second operation is permutation, where you permute rows of the matrix. Now remember, when you permute X, you should also permute B accordingly. But you will not permute the vector X. So this permutation operation, you will permute the rows in A and B, but not X. Right? This is a second legal operation. And at last we saw one more third legal operation that is very simple, that is called scalar multiplication. Unlike linear combination, when you do scalar multiplication, the scalar alpha should be non-zero. It can be negative, but it should be non-zero, right? Then we saw a protocol in applying these operations to obtain RREF. First, you will fill this. You will start making adjusting these entries to get into RREF in this order only. What is happening? Yeah. So you will adjust the entries in this order only. You'll stop. You will start from top left entry, make it equal to 1, and then you will make all the entries below the top left entry 0. Then you will go to second entry of second column. You will make this entry. You will try to make this entry 1. If this entry, if it happens that this entry cannot become 1, then you will leave it to 0. After you adjust this entry, you will make other entries below the second. I mean this entry 0. So in this fashion, you will adjust the entries in this order, right? Now, when adjusting, one important step is you should not undo an adjusted operation. You'll apply operations such that, let's say you are adjusting, this this entry here. When you are adjusting this entry, you should not this adjustment operation should not affect whatever work you have done in the earlier part of the matrix. That is one hard constraint you will always follow, right? You will apply the sequence of operations, then you will at last you will obtain a matrix which is in this format, in upper triangular format, where the leading diagonal entries are either 1 or 0, and all the entries below the leading diagonal are 0, right? I hope you are able to recall this exercise. Now, uh, to force you to remember, perhaps what I'll do is to solve a question. Let me take this question, right? Here, what are they saying? They have given three equations to us, and there are three unknowns here, right? Let me take this question. So first equation is x plus z equals 6. Second equation is minus 3y plus z equals 7. I'm writing it minus 3y because I want the order of the x to be x, y, and z. Okay. And third equation is 2x plus y plus 3z equals 15. 2x plus y plus 3z equals 15. Now, can somebody unmute and quickly tell me the ax equal to b format for this equation? So let me fill the obvious entries. So x, I want to fix the order as x, y, z. Okay. Then equal to b, because in the question we are fortunate that they have given the b in the right answer already. So let me fill the b vector right away. 6, 7, 15. Can somebody unmute and tell me the entries of x? Sorry, entries of a.
101,
101.
0 minus 3 1,
Very good. 0 minus 3 1.
2 1 3.
2 1 3. Correct. Right. This is ax equal to b. Now we'll follow the protocol. Right. First we'll start with top left entry. It is already 1, so there is no work to be done. Okay, sorry. Let me stick to the algorithm. First, I'll create the augmented matrix. A comma b equals 1 0 1 6. So this is what I mean. So when you create the augmented matrix, you will not put minus 6 here, right? You will put b as it is. Then second row will be 0, minus 3, 1, 7, and third row will be 2, 1, 3, 15. Now in this, if I draw the leading diagonal, if I draw the leading diagonal, let me increase the thickness. Yeah, if I draw the leading diagonal, it ends here, which means the adjustment should happen only in the this triangle, right? Now let's go to the protocol in adjusting these entries, right? First, this entry is already 1, so there's not much work to be done. This entry is already 0, not much work to be done. Now I will adjust third row first column, right? Can somebody suggest an operation?
R3, R3 equals R3 minus 2 R1.
Very good. Minus 2 R1, right? This will give me 1 0 1 6 0 minus 3 1 7, 2 minus 2 will be 0, 1 minus 0 will be 1, 3 minus 2 will be 1, 15 minus 12 will be 3. Right? Now we will go to second entry of second column. Can somebody suggest an operation? So always I told you to make an entry one. Easy operation to do is scalar multiplication. Right? So following that, what we will do, R2 equals R2 by minus 3. This will give me 1 0 1 6 0 1 minus 1 by 3 7 0 1 1 3. Now I need to make this entry 0. What shall I do? So remember, when you make this entry 0, you should not affect any of the entries that you have adjusted. So let me take a different color. Yeah, these entries should not be affected. Whatever operations you suggest, in fact this entry also, this entry should not be affected. Right? Now with this constraint, can you suggest an operation?
The R3 equals R3 minus R.
Yes, R3 equals R3 minus R2. If I apply this operation, then you get 1 0 1 6 0 1 minus 1 by 3 7 0 0, 1 plus 1 by 3 will be 4 by 3, 3 minus 7 will be minus 4. Right? Now only thing that is pending is I need to make this entry. I need to make sorry, I need to make this entry 1. To make an entry 1, an easy operation, a straightforward operation is as usual scalar multiplication. So what I will do, R3 equals R3 into 3 by 4. Right? If I apply this operation, the matrix that I will get is 1 0 1 6 0 1 minus 1 by 3 7 0 0 3 by 4 and um, minus 3. Right? Sorry, this should be 1, right? This should be 1. Minus 4 into 3 by 4 will be minus 3, right? Is it okay? I hope I have not done any calculation mistakes. Yeah, anyways, we will verify the answer. Now, are you all convinced that this matrix is an RREF? Yeah, I hope all of you are convinced. Now, once so why have we been doing this exercise? Why is RREF important, or why will RREF give us a solution to system of linear equations? Right? Now, to see how it helps, let me again write this augmented matrix in original matrix format. So currently I have this matrix A comma B that is reduced to row reduced echelon form. Now what I will do is to again write this equation back in Ax equal to B format. Okay. So now let me do that, and let's see if I write that, will I get any advantage in obtaining a solution easily, right? So let me write this matrix again. So 1 0 1, this will be A. I'm writing A. 0 1 minus 1 by 3 0 0 1 into x is x y z equals 6 7 minus 3. Okay. Now once you put this in matrix format, we can right away read the solution. Right? Now what I'm going to discuss now in obtaining solution is called as back substitution. Now the back substitution. So now you will start reading a solution from the last row. Right? Now when I multiply this vector here to the last row, what will happen is you will get this equation basically. When I multiply this vector with the last row, you will get 0 times x plus 0 times y plus z equals minus 3. Right, now you see what is happening, because you forced the entries below, entries below the leading diagonal to 0. When you apply this equation to the last row, you readily get the solution for z. Right, what is z? Z is minus 3. Right, now because z is minus 3, I know one solution to one variable. Then what I can do is to replace this z with minus 3. Right, once I replace this with minus 3, let us multiply this vector to second row. Then what will happen? It will be 0 times x plus y minus 1 by 3 into, now this entry will get multiplied by minus 3. Right, when you multiply this entry with minus 3, you get 1 plus 1 equals, and the constant here is 7. Now again, do you see what is happening? Because you had this entries below the leading diagonal to be 0. In this second row, basically, there are two coefficients that are unknown, but the value of the variable corresponding to this coefficient is already obtained from third row. Right, when you come to multiplying this row with this vector, you already had substituted value of one unknown. Right, that is why when you multiply this x with the second row, again you get only one unknown. Right, from this I can readily see that y equals 7 minus 1, that is 6. Right, now because I have obtained solution to y, let's substitute y here. What is y? Y is 6. Now let us multiply first row with the vector. Right, if I multiply first row with the vector, what I will get? 1 times x plus 0 times 6, 0 into 6 plus 1 times minus 3. This will be equal to 6. Right, now again here you see this equation has exactly one unknown. Now this can be easily solved, right? So x minus 3 equals 6, which means x equals 9. So the solution that I get is x, y, z equals 9, 6, minus 3. Right, now let us check if the solution is correct. Oh, solution is wrong with it. Yeah, I think I might have done some calculation mistake somewhere. Uh, oh, firstly, did I take the solution, I mean equations correctly? Yeah, sorry, sorry guys. I think I'm used to creating this silly mistake. So yeah, bear with me. 213 x y that is 6 7 15, and is somebody able to spot the mistake that we did? Minus 3 6, and if I substitute minus 3 minus minus 3 plus 9 is, yeah, this is matching. I think if I put x equal to solution that we obtained is minus 3 comma 6 comma, sorry, my pen is creating trouble. So minus 3 comma 6 comma 9, right? uh, just give me 1 minute, I'll connect the pen. Yeah, oh no, what's happening? Sorry about this. Okay, minus 3 comma 6 comma 9, right? When I substitute the solution, basically x plus z gives me 6. This equation is satisfied. Minus 3y plus z. Minus 3y is minus 18 plus z is 9. Plus 9 equals, sorry, this will become minus 3y will be minus 18 plus z will be 9. So this should give me 7. But this is giving me minus 9. That's all. So there is some issue in some computation somewhere. But I think nonetheless you get the point, right? How to solve the solution, how to obtain the solution. Is it okay, or is there any doubt? Is the procedure clear?
Yes, sir.
Yeah. Maybe let's take this as exercise, right? Let me again solve this question. You can also solve the question in parallel. Let's see we get the solution that we have in the web page. Should we do that? I'll solve in parallel. Perhaps this will be a good exercise for you also. You also solve in parallel. So this is a question. Let me solve it again. Uh, I encourage all of you to take a paper and again solve it along with me. That way, RREF will become very clear to you. You will not forget this, right? So 1, 0, 1 and B is 6. Then Z minus 3, 0 minus 3, 1, 7, 2, 1, 3, 2, 1, 3, okay. R2 equals R2 minus 2 times R1. This will be 1, 0, 1, 6, 0 minus 3, 1, 7. 2 minus 2 is 0. 1 minus 0 is 1. 3 minus 2 is 1. 15 minus 12 is 3. Then R2 equals R2 divided by minus 3. This will give me 1, 0, 1, 6, 0, 1, minus 1 by 3, minus 7. Did I do minus 1 by 3 there? Here is the mistake. Yeah, yeah. Here is the mistake. I should have done minus 1 by 3. Is it? Are you able to spot this? When I multiply R2 with a scalar minus 3, I should multiply 7 also with minus 1 by 3. I did not do this. That is why the answer is inconsistent. Now, is it okay to all? Like, are you able to understand where I committed a mistake?
Able to understand.
Yeah. Okay. So I think this is a good, like good warning that you should be very careful. All right. When you're dealing with matrices, please be very careful in gate, especially because it is a timed environment. It is very likely that you will create this kind of mistakes when you're solving in a hurry. Okay. Now for completeness, let me go ahead and solve this matrix, and I'll show you that we'll obtain the correct solution. Right. I'm doing minus 7 by 3 here, and let me copy over the row 3, 0, 1, 1, 3. Right. Then I need to make this entry 0. Then what I'll do is R3 equals R3 minus R2. So this will give me 1, 0, 1, 6, 0, 1 minus 1 by 3 minus 7 by 3, 0, 0, 1 plus 1 by 3 will be 4 by 3. 3 plus 7 by 3 will be 7 by 3 plus 9 by 3 will be 3 plus 7 by 3, right? Yeah, 16 by 3. Now I need to make this entry 1. So R3 equals R3 into 3 by 4. This will give me 1, 0, 1, 6, 0, 1 minus 1 by 3 minus 7 by 3, 0, 0, 3 by 4 by 3 into 3 by 4 will be 1, 16 by 3 into 3 by 4 will be 4, right? Yes. Now I'll bifurcate this matrix into Ax equal to B. Then what will happen? 1, 0, 1, 0, 1 minus 1 by 3, 0, 0, 1 into x yz equals 6 minus 7 by 3, 4. Hopefully I have not done any mistakes now. Yeah, I think from here if you do back substitution, you will get the answer. Okay, I hope this is okay. Uh, okay, let me take. Now from here I want to discuss a concept called rank. So today I would like to start with a fresh concept called rank. So okay, first of all, is there any doubt in this RREF and obtaining a solution to system of linear equations?
No, sir.
No, good. Right. Now, how many of you are aware with rank? Aware of rank? Rank of a matrix. How many of you are aware of rank? Or should I cover from start?
Double T.
Okay, I'll cover from start. So, uh, when you solve system of linear equations, when you convert this a comma b, you have this augmented matrix a comma b. No, if you convert this a comma b to RREF, what will happen if you encounter a row that is all zero? What happens? So I'm not giving definition of rank as of it. Let me motivate rank. Fine. So what happens if any row of A, let's not worry about B portion as of it. Fine. You will see RREF will always convert the augmented matrix. Now in this conversion of A comma B to RREF, I want you to put your focus on the matrix A only. Right. A question I ask is, when you convert this A to RREF, what will A comma B to RREF? What will happen if any of row A is all zeros? What does that mean?
Determinant would be
Exactly. Determinant will be zero. Right. Now let me give a simple solution where determinant will go to zero. Right. Let's assume you are given a system of equations. Let's say x plus y equals 3, 2x plus 2y equals 7. Right. Now let me take the augmented matrix for this. Augmented matrix will be 1, 1, 3, 2, 2, 7. Right. Now if you want to convert this to RREF, what you will do is to make this entry 0. Right. To make this entry 0, you will multiply R2 equals R2 minus 2 times R1. And when you do that, you will have 1, 1, 3. Observe that 0, the second row will become 0, 0. 7 minus 3, 7 minus 2 into 3 will be 1. Right. Now this matrix is already in RREF format. Why? Because the leading diagonal is already in 1 comma 0 format, and all the entries below leading diagonal is already 0. Right. Now here you encountered a matrix where all rows of A are 0. Right. Now our friend told that if all rows of I mean, sorry, I said all rows of A. No, no. So the all entries in some rows are 0. Right. When this happens, our friend told determinant of A is 0. Is it the case? If determinant of A, that is determinant of 1, 1, 2, 2, is it 0? Yes, right? This is 0. In fact, that is true. When you encounter a matrix, when you are given a matrix where when you apply the procedure to obtain RREF, in that process, at any step, if all the entries of A, sorry, not at any step, at the final step, when you converted this matrix to when you have an upper triangular matrix in the final step, when it if it so happens that all entries in any row of A is all zeros, then that matrix is not invertible. Right now, a natural question is, what is the consequence, right? What's the consequence? So let me take a easy case first. Now, what will happen if A is invertible? See, one thing we are doing is we came to this RREF exercise basically for two reasons. One reason is when A is not invertible, right? You can always keep these two reasons in mind. You come to this RREF for two reasons. One is when A inverse does not exist, and second reason is computational reasons, right? If A is invertible, if you ignore computational reason for a while, then you know that solution is nothing but x equals A inverse B, right? Do you recall that x is A inverse B? Okay. So now x is A inverse B. Now let me ask you a question. Given a matrix A, is A inverse unique? Is it unique?
Yes,
Yes.
sir. It is
Yes,
unique.
it is unique, right? Now, what can you tell about system of linear equations when? Okay, before that, I'd like to tell you one concept. So we saw that if any row becomes all zeros, then we saw that A is not invertible, and the converse is also true. Sorry, not converse. So if it happens that in the RREF there is no row that is all zeros, then basically it means that A is invertible. Right? Let me tell this statement to you. If in the row reduced echelon form, in the final step of RREF procedure, if there exists no row in just the A part, ignore about B part for now. If there exists no row in A that is all zeros, then A inverse exists. Okay, does this statement make sense to you? Is there any doubt in this statement? Okay, good. So then A inverse exists. Now we just saw if A inverse exists, then A inverse should be unique. Should be unique for all A that are invertible. That are invertible, right? And what do we mean by that are invertible? So basically, determinant of A should be greater than zero. Sorry, not greater than zero. Determinant of A should be not equal to zero. For any A such that determinant of A is not equal to zero, A inverse should be unique, right? Now, what does that mean if A inverse is unique? So we know that solution to X is A inverse B, right? And B is given in the question. B is given in the data, and we know that A inverse is unique. Now, can you comment on nature of X? Is X also unique?
Yes, sir.
Exactly.
Very solution.
Yes. Right. So then I can further refine this statement. Right. in the final step of RREF procedure, if there exists no row in the A part, forget about B part, if there exists no row in the A part, that is all zeros, then A inverse exists and solution X is unique. Solution X is unique. Does this make sense? Okay, I think all of you are convinced with my statement. Now, earlier we took one system, right? We took this system x plus y equals 3, 2x plus 2y equals 7. Now, in this system, what is happening is in the A part, we encountered a row that is all zeros. Then, what can we comment about x? Right? Let me actually copy over this RREF format of the given question. I'll just copy this matrix below 113 0 0 1. Right? 113 113 0 0 1. So remember that this is the A part. Let me highlight the A part. This is the A part. Right? Now we encountered a case where all elements of some row in A is 0. Now, see, one thing is if you ever encounter such a case, then only two cases are possible. One is you have infinitely many solutions, and other cases you have no solution. Right? Earlier we saw a case where you have unique solution. So from these three conditions, you know that there exists no such linear system that has greater than one solution, but only finitely many. This case will never happen. Either you have a unique solution, this case will never happen. For any linear system you take, you can take any number of toy examples and you can check, right? Either the system will admit infinite solutions or the system will not have any solution or the system will have a unique solution, right? Now what I'm saying is for unique solution, we already saw the condition. What is the condition? In the RREF matrix, there should be no row that is all zeros in the A part. That is when system has unique solution, right? Now immediately it is very clear that for you to fall in one of these two cases, then you need to encounter a row that is at least one row that's all zeros. Now to differentiate which matrix falls into which of these two cases, we need a concept called rank. Right? Now formal definition of rank comes from eigenvalues, etc., etc., but here I don't want to get into that. Right? Formal definition of rank is, for those of you who remember eigenvalues, formal definition of rank is number of non-zero eigenvalues. But for this class, just believe me that rank of a rank of a matrix. Let me write this statement. Rank of a matrix A such that A is in RREF. A is in RREF equals number of non-zero rows in A. Right? See, this rank equals number of non-zero rows is applicable only for matrices that are in RREF format. Right? For an arbitrary matrix, you cannot claim rank to be number of non-zero rows. Okay. Now, I think is there any is the definition of rank clear for only for RREF matrices? Is it
Yes,
definitely
sir.
yes? Now, can you tell me? Yeah, let me ask you a question to kind of probe you if you understood the rank definition. Let's say you're given a system AX equal to B, okay, such that the solution X is unique. Let me give dimensions of it. Let me refine the question. Sorry. Let's say you are given a linear system of n equations and n unknowns, right? For this system, it happens that the solution is unique. Let solution be unique. Now, can somebody say what is rank of A?
Sir.
And
N. Why is it n?
because because the solution is unique,
Hmm.
then the all the rows will be non-zero.
Exactly, right? So basically, rank of a solution, rank of a system that admits a unique solution equals n, where n is the number of unknowns and number of equations, right? Now, so this is your unique case. Now, earlier I was telling that you have two other cases. Now, these two cases are possible only if rank of A is less than n. Is this clear? Because if rank equals n, you already know it falls into the unique solution case. If rank of A is less than n, you need to inspect one more condition to classify if the system admits infinitely many solutions or no solution at all. Right? Now, to find out if it is infinitely many or no solution, you need to compare rank of A and rank of augmented matrix. Rank of A and rank of augmented matrix. Okay. Now, one thing is you see one thing, this equation is always valid. Rank of A can only be less than equal to rank of B. Do you see that? Sorry, rank of augmented matrix A comma B. Do you see why? It can never be the case that rank of A is greater than rank of A comma B. It can never be the case. This case is not possible. Are you able to see why this case is not possible?
No, sir.
No. Okay, let me give a illustrative proof. Let's say this is a matrix, right? Let's say this is your A matrix. Let us assume that number of non-zero rows are below this entry. Now let's assume that below this entry all the rows are non-zero. Sorry, all the rows are zero, right? Now let me give dimensions to this. So this the A has n rows, and basically you have m less than n non-zero rows. What do you mean by non-zero rows? At least in each row there is at least one entry that is non-zero, and you have n minus m rows that are all zeros, right? And further, remember that because we are dealing with this rank, basically we are in the RREF format. That should always be at the back of your mind. Okay, this claim that I make is only true for RREF matrices. Actually, I'm not sure if it holds for other matrices also. I have to think about it. But nonetheless, this claim is true for RREF matrices. Okay. Now, what I'm doing is to append a column to this. Right. Now, can somebody tell me if I append, no matter, let's say I append a zero, non-zero, whatever I append, will this row all of a sudden become zero? Will any row in the top m rows all of a sudden will it become zero? No, right? Because see, this row is in the m part because there was already some entry in A that is non-zero. Even if you append a zero here, it is not going to affect the rank of A comma B. Do you see what I mean? This row in A comma B will also be non-zero because there is at least an entry in the A part of this row That is non-zero. Is the argument clear?
Yes, sir.
Yeah. So that is why, see, one thing is in the A comma B also, because it is, you're just appending a column, you're just appending B to it, right? In A comma B also, the first m rows are going to be non-zero. M rows are non-zero because they are anyways non-zero in A. Now let us see what will happen to the remaining n minus m rows. Now see here, if you append, if this entry is zero, then because all these entries are zero, this row will also be all zero row, right? But in the new column, let's say you append a non-zero row. Let's say you append one here. Then what will happen? This entry, this row will become a non-zero row. Do you see what I mean? So in the A part, corresponding to this row, you found all zeros. But by appending this new column, and let's say you appended a non-zero entry here, then this row will shift to the above part. That is non-zero part. Is the argument clear? Or is there any, should I repeat? Is there any doubt? Actually, this is kind of important. If there is any doubt, please let me know. I'll repeat this if there is a doubt. Am I still online? Utkarsh, was it clear to you?
Yes, sir.
Yeah. And Shashikant?
Yeah, actually, I'm participating in multiple sessions basically. So,
Oh, okay, okay, sure.
yeah.
Then I'll assume that this is clear to you. So basically, this inequality is always true, right? Now, let me summarize the story so far. We know the condition when x is unique. The solution x is unique. Now we need to find out when is solution x infinitely many and when there exists no solution, right? It turns out the condition for infinitely many is when rank of A equals rank of B. Sorry, rank of A equals rank of augmented matrix A comma B, right? And you get no solution when rank of A not equals rank of A comma B. Okay. Now, as a before we conclude the session, let me go back to the simple system that I gave you. That is two equations and two unknowns. Let's take the system. So here, what is happening? Yeah. First of all, what is? Can you tell me the rank of A and rank of A comma B for this augmented matrix? I mean, the RREF reduced augmented matrix. What is rank of A?
It's the rank of A is 1 and
Yes.
rank of augmented matrix is
Rank
2.
of augmented matrix A comma B is 2, right? Now here we encountered a case where R of A is not equal to R of A comma B. So then, according to my formula there, then basically this system is um, no solution. No, as a simple exercise, let me give you this equation once again and see if you are able to find a solution to the system using a pen and paper. X plus y equals 3, 2x plus 2y equals 7. Let me know. I'll give you 2 minutes. Let me know if you are able to come up with a solution to the system.
It's no solution.
No solution, right? Yeah. So basically, the system does not admit solution. Now let me correct this equation and let me see if you can come up with a solution, right? Let me make this 7 to 6. Now can you come up with a solution?
So now there will be infinitely many solutions.
Exactly. There will be infinitely many solutions, right? For example, one such solution can be 1 comma 2. Other solution can be, let's say, 0.5 comma 2.5, right? In fact, let me convince you that any solution, any x comma y, such that x plus y equals 3. If you simply satisfy the first equation, any solution that satisfies the first equation will satisfy second equation also. Why? Because simply second equation is a scalar multiple of first equation, right? I can write the second equation as 2 into x plus y equals 2 into 3, right? Now here, if x plus y equals 3, if x plus y equals 3, basically 2 into x plus y will be equal to 2 into 2 into 3, right? So this using intuition, you're able to tell that this system has infinitely many solutions. Let us see what will happen to the RREF format of this, right? So the augmented matrix will be 1 1 3 2 2 6. What will be the operation you do? You will do R2 equals R2 minus 2 times R1. When you do that, you will get 1 1 3 0 0 and 0, right? From this you see that R of A is 1 and R of A comma B equal to 1, right? And because this is you encountered a row that is all zeros, unique solution is ruled out. And since R of A equals R of A comma B, you have infinitely many solutions, right? Yeah. So before we conclude the session, I'll simply let me recall what all we have done today, what all we have seen today, right? So we started with RREF. From RREF, what we did is we did back substitution. Once we did back substitution, we saw how to obtain solution x, right? Then further we saw that your solution will fall in one of the three cases. What are the three cases? Either x is unique, or you have x is infinitely many, or no solution, right? When is x unique? It's x is unique under only one case. That is when then when I can simply write rank of A equals n, where n is a number of unknowns or number of uh, right. Or to be more formal, or, more, or to be more specific, when x is unique when number of non-zero rows in row reduced echelon form of just the A part, not you will not include A comma B. If row reduced echelon form of A part is equal to yeah, if in row reduced echelon form of A, there is no non-zero row. Sorry, there exists no zero row. Let me repeat. So you will say x, this system of linear equation admits a unique solution when in row reduced echelon form of A there exists no row such that it is all zeros. That is when you will claim that x has unique solution. If there exist zero rows, then we know that we know that the system admits either infinitely many solutions or no solution. When will it admit infinitely many solution? When rank of A equals rank of the augmented matrix A comma B. It will admit no solutions when rank of A not equals rank of A comma B. And further we saw that one inequality always holds, that rank of A comma B is always greater than equal to rank of A. right? Is this diagram clear to all? Is there any doubt? Yeah. Okay. I assume there is no doubt. Actually, from going forward, from next class, we will solve previous year gate questions. So I had a meeting with other NPTEL authority and other gate TAs. It seems that we are supposed to solve gate questions. So this will be the last teaching kind of session. From next class onwards, I'll take previous year gate questions in linear algebra and solve them live in live class. So then for the solution to to make total sense to you, it is good if you come prepared with the topics to the class. Okay.
Okay.
Sir, could you please suggest a book for this subject as well as for computer
Okay.
projects?
So yeah, see, I fell in love with linear algebra because of Gilbert Strand.
I feel I mean MIT OCW will be
Exactly.
there.
MIT OCW, or you can go to YouTube also. So Gilbert Strand linear
Yeah,
algebra.
Gilbert Stein.
Yeah. So I cannot think of a better resource than these videos. Right? There are 35 videos. You can simply binge watch the lectures. And this professor explains so well that once you watch these videos, yeah, he really made me fall in love with this subject. So I think you'll also appreciate this. Okay, he teaches us in a very intuitive format. Any other questions?
Sir, could you also tell some other source for other subjects, especially combinatorics and probability?
Probability at a advanced, I mean at a graduate level, I used to follow this textbook. Yeah, probability again, there are videos, but I'm not sure how much of it is required for gate. But if you want to learn probability, I would really suggest this course, Probability by CC Cliss. There are 25 videos here. Maybe I'll paste the link in
The
the
following
Meet
content is
chat.
provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer.
Yeah. I'm pasting
So
the link in the Meet
this
chat.
is very in-depth course.
This in-depth course actually, yeah. So this is a course that I studied probability after joining masters. So I don't know how much of it is required for gate. But nonetheless, if you want to learn probability, end to end, I would say that this resource is very good. Okay. Actually, in the meeting, they were telling me that there is this syllabus mapping. Perhaps you can follow this also. Yeah. So if you go to gate.nptel.ac.in, right, you see a tab Gate syllabus mapping, right? In syllabus mapping, once you go to computer science, you can select topic. For example, you are asking probability, right? So let's say I select engineering mathematics, and here I select probability and statistics. Once you select this, they have given mapping from topic to video, right? So for example, this lecture that is on random variables. You click this lecture, and there is an NPTEL lecture on random variables. Then you have probability distribution, normal distribution, etc., etc. You can also follow this mapping.
And
Hmm.
are there going to be any mock tests for computer science, because I'm not able to find mechanical, civil, and electrical.
Okay.
Yeah, I mean, I think I made the request for that at NPTEL page as well. I mean, if number of students do the same thing, so then it will be more effective.
Mhm.
Okay.
Oh, these are the mock tests, is it? And get practice test. Go to course. Here's about.
So these session will be continuing till the gate exam, right?
I'm not sure. So my commitment was 1 semester. That is 6 months. After this, I'm not sure if somebody else will take over.
No, no.
Huh.
I'm saying that like you just started. I mean, this session is started. I think we have 5 to 6 sessions.
5 to 6 sessions currently. Yes,
So
yes.
almost a month.
Correct,
So
correct.
I mean, you will be available till I think February to get exam.
Not till gate exam, maybe until December I may be available. I'm not very sure. I have to ask NPTEL people.
Okay, okay.
Yeah.
So I mean, will there be? I mean, because as you are single TA available right now,
Hmm.
so I mean, is there possibility that there will be no TA in just uh, January or February?
Yeah, I think this question should go to the NPTEL people. Yeah, yeah.
That will be time when we have to discuss a lot of things
That's
just
right.
before examination.
That's right. That's right.
Sir, one more question regarding this linear algebra course.
Yes, yes.
Uh, for example, by browsing on internet and all, I was able to find some book suggestions. Of course, I will consider your Gilbertstein videos also.
Yeah.
Uh, just I was telling that, for example, if we take a book called Hoffman Kunze or even
Oh
even
no, no, don't do that.
Gilbertstein, so
Huffman Kunz is a overkill.
they start and they discuss a lot of theorem and proofs at the start.
Yes, yes.
So
That's what I'm saying. Huffman Kunz I read during my masters. Actually, even I found it really difficult to follow the book because they teach linear algebra in a very theoretical manner.
so as far as gate is concerned, theorems and all are not much required. Only application based we have to
You just need to
understand.
understand the intuitions of theorem. See, one thing is they can only ask MCQ questions, right? Then these questions are ruled out. They cannot simply tell, okay, is this theorem valid? Or they cannot ask you to write a formal proof for the theorem. है ना? Then all you need to understand a subject at an intuition level. You need to understand the theorem and you should be able to apply the theorem to problems. Right?
Yes, sir.
Yeah.
Yes, sir.
No, so one thing I would suggest is actually I was going through this website called Gate Overflow. I'm not sure if you know about it. In this Gate Overflow, they have compiled a book that contains previous year questions. Let me show that to you. Yeah, I think volume one is mathematics. Yeah. So here, one thing I liked in these books is they have combined. For example, we are seeing linear algebra, right? Where is the LA? Mathematical logic, set theory, calculus. Yeah, where we are discussing linear algebra, right? So here they have given like from LA, what is the minimum and what is the maximum that you can expect. They are given the mark distribution, and moreover they have to, also organize the previous year questions in terms of concepts. Now, for example, today we saw we have completed system of linear equations, and we saw rank of matrices today. Although not in a formal manner, I motivated rank from the RREF of an augmented matrix. Right now, once you understand the concept, you need to look at the solution, look at the questions, and solve them. Right? Actually, yeah, maybe in this session, let's see what is the solution to this question. Suppose P is a 4 cross 5 matrix such that every solution to Px equal to 0 is a scalar multiple of 2, 5, 4, 3, 1. Then the rank of P is what? Can somebody answer this question? Uh, can you try this question? Or should I try this question? Okay. Anyway, so what I'm saying is, once you go through the video or attend this class or anything, you will get you will be able to crack gate only when you solve the previous year gate questions. That practice is very essential, right? Yeah. So this is one such a great resource for computer science. You can take other resources also, whatever makes you feel comfortable. But I insist from first class also. I have been insisting that solving problems is the key to cracking it.
Is the answer here four, sir?
Yes, answer is let me verify. Correct. Answer is four.
I have a request.
Hmm.
In automated theory, I'm finding it difficult to understand the uncertainty problems.
Yeah.
So can
Problem
you
is yeah. Actually, in that meeting, problem is it seems that I will cover LA questions only.
yeah? So I mean,
Yeah.
if you can suggest some reference like
For TOC,
access. So,
TOC actually that Aho Ullman, that book is a great resource.
yeah, I mean,
Uh,
I have it, but this section, this uncertainty problems have kind of very theoretical aspects of it.
okay, okay.
So
Uncertainty.
it's difficult for me to understand.
Actually, during my preparation, right, for uncertainty, actually, yeah, let me end the session. These are some tips I want to give, maybe not officially for